integration of a linear function of x. Here, there are some functions of differentiation that we cannot integrate the functions directly using that method that we just treated, which is polynomial function. But we can substitute. We substitute to replace x in this function, and it will take us back to that polynomial function we just differentiated, and we can now use polynomial function to differentiate such function directly and replace our substitution. So here we have if you have integral of x raised to the power of n with respect to x. Actually, if we integrate this, we are going to have x raised to the power of n plus 1 all over n plus 1 plus c, right? And if we also integrate exponential x with respect to x, we are going to have exponential x plus c. So this is appropriate to x. So to integrate this and this function, we need to find a way to reduce these two functions to this form. And if we reduce this to this form, we can easily get our integration. And to do that, what do? We have this. So like a, this is our a here. We have integral exponential 5x plus 4 with respect to the x. So we can say let our u be equal to exponential, let our u be equal to 5x plus 4. That is this upper value. We can let our u be equal to this. So if our u is this, then you agree with me here that this exponential 5x plus 4 with respect to the x will now be equal to integral exponential u with respect to the x. But there's no way we can integrate exponential u with respect to x here. And we have to replace the value of the x here. And to replace the value of x here back to the u instead of the x, we differentiate this. And when we differentiate this, we are going to have the u, the x equal to, differentiate this will give us 5. And the derivative of constant, which is 4 here, is 0. This is over 1. And to cross multiply, we have the u over 5 equal to the x. So this, the x, can be replaced by the u over 5 from this new function we just derived. So we have from here as integral exponential u times the x here, we are putting the u over 5, the u over 5, and this is the same thing as you can take this 5 outside, which is 1 over 5 integral exponential u with respect to the u. So this now is the same thing as this. So exponential integral of exponential x will give you exponential x plus c. Likewise here, exponential u will now have 1 over 5 then times exponential u plus c. But don't forget, we substituted u for this function here. So we need to replace the value of u by this. We now have integral, the original question, which is exponential 5x plus 4, the x equal to 1/5 exponential 5x plus 4 plus c. So always remember to put c. That c is very, very essential. So that is the answer for that. And to solve this, we are going to use the same method. Apply the same method to solve that. We have integral 2x minus 7 all raised to the power of 3 dx. So we say let u be equal to 2x minus 7, so that this will now be integral u raised to the power of 3 dx. So this value of the x, we need to replace it by differentiating this. Here our du dx will be equal to, when you differentiate this, 2, differentiate 7, 0. So this is over 1. If you make the x subject to formula, because of this, we now have our du over 2 equal to dx. Then from here, we now have integral u raised to the power of 3 times this dx is our du over 2. Du over 2. So this will give us, when this comes out, this integral u raised to the power of 3 du. So this function, if you take a look at this function, everything here is still the same thing as this method. So all we did is we just replace the value of x here by this, like this. So, and that is why we have this. So this will now give us 1/2, then times u. Don't forget, we are adding 1 to be 3 plus 1 over 3 plus 1 plus our constant term. And this will give us half. This plus this will give us 4. And 4 times this will give us 1/8, then u raised to the power 4, then plus constant term. Don't forget, our value of u is this. So we have to replace this. This will give us 1/8. Then u, instead of writing u, we are writing 2x minus 7 all raised to the power of 4 plus c. So this is the integration of this. And that is how to integrate that method. Another aspect of integration we need to consider here is the integration of the form. Integration of the form integral f prime of x over f of x with respect to the x. So look at this form on board. That f prime is also known as dy dx of the function of x. That is f prime of x. Don't forget, this is the same thing as dy dx. That is the derivative of function of x is written as f prime. And if we integrate f prime of x, that is, if we integrate it, it's the same thing as if we integrate this, right? So this will give us a function. We got to have the function back again. That is, if we differentiate, we have f prime. And if we integrate f prime again, f prime of x, we get this. So if we integrate this as well, you know we have y. So there are some functions like that which, if you want to integrate, we need to consider this form, and then we can get our actual value. This is what I'm trying to say. Let's say we have this. Let's say we have this. Example: if we have a integral 1/x with respect to the x. I want to integrate this. there is no way I can apply the polynomial function here, because if I try to do this like, if I want to do it like this is the same as x to the power minus 1 with respect to the x, right? And this is more or less like polynomial functions, what we just did. And this, if we try to do it like by adding 1, you know, we have x to the power minus 1, then plus 1. All over minus 1 plus 1 plus c. And this will give us x to the power 0 over 0 plus c. So this method is crazy, very, very wrong. You cannot apply it like this, because this function will be undefined as we try to get the solution to this using this procedure. Therefore, we need to consider this standard form of integration. And what is this actually saying? What we are saying here is, let's say we have a function. We have two functions now. This is differentiated function and this is ordinary function. I want to integrate the two functions now as a fraction. You consider the denominator. If we differentiate the denominator, are we going to have the answer for the numerator? If the answer is yes, then we are going to take the substitution method that we just treated here. We are going to apply this substitution method of linear function to get that function. But if it's not like that, then we apply another procedure. So this is what I'm saying. This is very wrong, like I said. It's very wrong. So we cannot have it like this. So what I will do now is, if we differentiate this, if you say let our u be equal to x, if we let u be equal to x here, then if you now differentiate the u, the x here, this will be 1, right? I want to get this function, the x. So by cross multiplying, we have the u equal to the x. Therefore, this can also be written as integral 1 over u times the u, right? Very crazy, it's still the same thing. So instead of for us to waste our energy, we are actually saying if we differentiate this, we are going to have 1. And what is the numerator? Is 1. If we differentiate this, we are going to have f prime of x, which is the same thing as the numerator. Differentiate this, we have this. I think the derivative of this denominator is equivalent to the function at the numerator. Then, if you have this form of this, you can easily say the answer for this is ln of function of the denominator plus c. That is what you are trying to say. So this is the same thing as in what? X plus c. That is what you are trying to say here. That is, when you differentiate x, the answer will be 1. And the derivative of this is 1, which is the same as the numerator. Then we can take the length of the denominator, which is our final answer. So let's apply it to some functions so that you understand what I'm saying better. So let's look at more examples. Let's say we have so integrate the following functions. We have a, we have a 2x plus 1 all over x squared plus x, and b, we have x squared over x cubed plus 7. We have c, we have a 6 x plus 5 all over 3 x squared plus 5 x plus 7. So to solve this now, let me solve one from this question. If I solve A, I will have integral 2x plus 1 over x squared plus x with respect to the x, right? If we differentiate to x squared, we are going to have 2x. If we differentiate x, we are going to have 1. We can see that the derivative of the denominator is the same thing as the function we have at the numerator, which is what this is saying. That shows this integration is in standard of this. And how do we move further? So we can now say let our u be equal to x squared plus x. We want to find the x here, so the u, the x will give us 2x plus 1. So by the time we cross multiply, this is over 1, so we are going to have the u over 2x plus 1 equal to the x. So this will now be equal to integral 2x plus 1 over u. We replace everything here by u, then times the x. This is our ds, the u over this, the u all over 2x plus 1. So what will happen here is this will take care of this. We now have integral 1 over u, then the u. And this is in standard form of this. So we can now see this is the same thing as in ln u plus c. C is a constant term. So we got to replace the value of u. And what is our u? Our u is x squared plus f. So this will give us ln x squared plus x, then plus c. So that is the answer. So when you have the derivative of the denominator equal to the function at the numerator, you take the